I want to talk to you about intelligent life in the universe, and I hope my okay, it doesn't work. Well,
much about intelligent hardware.
Yes, it's always, well, one can also do it with just typing written here. Okay. Okay, what do we know about extraterrestrial intelligence? Man has always thought about the existence of non-human intelligent beings like gods, angel, demons, centaurs, or these UFO reports. What does science say about this? Unfortunately, we have to say that no contact exists with extraterrestrial intelligence, and no trace of their existence has ever been found. One can even give a sort of proof that this is the case, because if you would find an artifact which could be identified as beyond human engineering, you could sell it at international auctions for billions of dollars, and I think Bill Gates would like to buy it for that amount of money, and nobody could ever resist having $1 billion on one's bank account. But still, we have to say that it's almost certain that extraterrestrial intelligent civilizations exist. There are three arguments for this. One is the astronomical argument that a very large number of Earth-like planets exist in the universe. The biological argument that once given an Earth-like planet, there is a high likelihood that life and even intelligent life will form on it. Now, if you have that many extraterrestrial civilizations, the question arises, why don't we have contact? And this is the so-called Fermi Paradox, and I think an explanation can be given if you carefully think about the nature of extraterrestrial life. Here you see a map of the Earth, and plotted the mean annual isotherms, and here in the center of the Sahara you see a red region which encircles the region where you have more than 25 centigrade annually, mean annual temperature. There are very few people live there, and also very few animals and plants. So this is essentially almost devoid of life. A similar region is the Arctic region and the Antarctic region, extending from 60 degrees northern and southern latitudes. And because cosine of 60 degree is 1/2, this tells you that life is very sensitive to the solar radiation, and the solar radiation can change only by a factor of 2. And translate this into the solar system, you find this is roughly from 7 to 1.4 astronomical units, which is roughly the region between the orbits of Venus and Mars. Now, I don't want to talk more about habitable zones because there will be a talk on this. I only want to mention that time-dependent effect narrow this region very much to the so-called continuously habitable zone, which is around the Earth's orbit, 0.95 to 1.01 astronomical units. Now, there is another problem for life existing on planets, and this has to do with the tides. Here you see the Earth at a distance of 1 astronomical unit. When you bring it closer to the Sun, the tides, which are due to the divergence of the gravitational field, which rises with a third power of the distance, get very much bigger, and there is a distance of 0.6 astronomical units, where in a billion years the tides are so strong that it would halt the spin rotation of the planet, and that co-rotation, at the co-rotation distance, you would have then a planet which always faces one side to the sun and the other side always away from it. On such a planet, the oceans would evaporate and deposit on the backside of the planet, and life would not exist. Now, how can we translate this now to other stars? Where is this in other stars? Now, the other stars can be differentiated by the spectral type. Oh, be a fine girl or guy, kiss me or something like this, and you see that O stars, this is a temperature classification, so the O stars have very hot surface temperature of 35,000 degrees, and the habitable zone is far out, 400 to 800 astronomical units. The Sun is a G star, which has 5,400 surface temperature, and here we have just seen it. The habitable zone is 0.7 to 1.4 astronomical units, and when you go to M stars, which are cool, 2,600 degrees surface temperature, there the habitable zone is between 0.6 and 0.1 astronomical unit. Now, in order to have intelligent life on a planet, it will take a long time, and on Earth it took 4.6 billion years, and therefore the planet, the central star, has to live longer than this. So O stars have only a lifetime of 1,000,000 years, so they certainly cannot be seeds of life, and even F stars, for F stars, the lifetime of the star is not long enough to develop intelligent life. So these stars are excluded, these types of stars. That doesn't matter much because the F stars are the most frequent. 4% of all stars are F stars, and the rest is even less, so we can forget about these type of stars as seeds of life. But the problem with the co-rotation radius is a much bigger one. Here you see for the M stars, which are so close, the habitable zone is very close, far inside the co-rotation radius, and therefore planets orbiting here in this nice temperature zone will co-rotate, and therefore life will not be there. And the same thing happens for the K stars, and here we have a big problem because 72% of all stars in the galaxy are M stars and 40% K stars. So what you conclude from this graph is only G stars are the ones which are expected to be seeds of life, meaning the planets orbiting G stars. Now, you need now the probability that some terrestrial planet will orbit a G star and be in the continuously habitable zone. For this, I have to go a little bit into planet formation. Here you see the spiral galaxy M74. Our Milky Way would look quite similar to this. And the outstanding thing is the spiral arms here, but what we are mostly interested in are these very dark dust clouds, which are associated with large molecular clouds, which are the seeds of star formation. Here you see from radio observations, radio line observation, the outline of one of those large molecular clouds, and these are very cold, and because of dust they shield the inside from stellar radiation, and they have very dense clumps and cold clumps, which when they are disturbed in some way start to collapse due to their own self-gravity. And this collapse happens rather rapidly, about 500,000 years, and the radius changes by a factor of 1,000, and already here you have a little rotation, or everything rotates in the galaxy and this rotation gets strongly amplified because of conservation of angular momentum, and as this collapse is not a homogeneous collapse, but very inhomogeneous, you develop an entire star cluster, and you get individual blobs, and these individual blobs themselves developed into accretion disks in which you form a protostar in the middle, and then this plate-like thing fanning out these accretion disks. And in this accretion disk you have a dust lane and the equator, in which dust accumulates and dust coagulates and forms in time scales of 1,000 to 100,000 years, forms planetesimals, which grow to sizes of a kilometer to 10 kilometers, and they then eventually, in 10 million years or so, accumulate to planets. Now, here you have a somewhat older calculation which shows the planet formation in a rather nice way. Here you have the different types of stars, and here the distance in a logarithmic scale, and you have two interesting lines, this green line and this red line. The green line separates the region close to the star. We are only interested in the G stars, as you have heard. There the temperature from the protostar heats up the accretion disk. The temperature is so high that dust evaporates, and therefore no planetesimals are here. And so from here on then you have the terrestrial planets, and then you come to the red line, and this is the ice formation line. There the temperature in the accretion disk has dropped below 170 degrees Kelvin, and here then ice crystals develop from the rather abundant water vapor in this accretion disk, and they quickly grow, these terrestrial planets which form there, grow accumulating ice crystals, but then you get masses of the order of 5 to 10 Earth masses, and these masses are then become so big that the gravity is enough to now accumulate also hydrogen, the most frequent material in accretion disk, and helium, and then quickly in a runaway accretion form Jupiter planets of the order of 380 Earth masses, also in about 10 million years. Now, there is no life on these planets. Out there you have smaller objects, because there you are at the end of this blob from which all this formed. Now, we come to an equation which I have the honor that Francis sits here, who was the originator of this type of equation. Let us estimate how many Earth-like planets can we expect in our galaxy. You start off with a number of stars in our galaxy, 1.6 times 10 to 11, and we have to multiply this times 0.1 to account for the fact that we are only interested in G stars. Then we multiply with 0.6 because we need population 1 molecular metal abundance. Only metal-rich material can form big enough terrestrial planets. You multiply times 0.3, which is the rate of single stars, because 70% of all stars formed are members of binary or multiple star systems, and we want to have a very secure and safe development of planets. So we exclude multiple systems. Then we come to the probability that a terrestrial planet is just in the continuously habitable zone. This zone had a diameter of this amount, and you divide by the distance to the ice formation radius, and because there are 4 terrestrial planets or so formed, you multiply times 4, and then you come finally to this rather severe factor back there. This has to do with the migration of Jupiters. You know that in 1995, the first extraterrestrial planets were discovered, and these were of Jupiter's size. And the surprising thing was found that we have now about 300 of these objects, that most of these orbit very close to stars, much closer than the ice formation distance. Now, why are they found so close to their central stars? The reason and the answer is they migrated from the ice formation distance down to these distances. Now, how can you migrate? I mean, you cannot trick the law of angular momentum. So what you do is you have a massive accretion disk, and you have many planetesimals, and these Jupiters throw out planetesimals from the inner parts outside, and this way can lower their angular momentum and spiral in. And on their way doing this, they eat up all the terrestrial planets on their way, and no life will then be possible because they have all been swallowed by the Jupiters. So this 0.303 is the factor of accretion disks which have the fact that the Jupiters don't migrate. So some have just the right mass where this Jupiter migration does not happen. So when you do all these calculations, you find 4 times 10 to the 6 habitable planets in our solar system, in our galaxy. This looks like much, but actually you find that among 50,000 stellar systems, only one has a planet in the continuously habitable zone. So this is not much compared to the number of stars in our galaxy. But if you multiply with 10 to the 11, which are the number of galaxies in the universe, you have 10 to the 17, 4 times 10 to the 17 Earth-like planets in the universe, and this number alone tells you we cannot possibly be alone in the universe. Let me now come to the second part of my talk. Take an Earth-like planet. How probable is it that life developed on it? Here we have to get the information from the early history of our Earth. And if you look at this very early time, in the so-called Hadean time of Earth evolution, you will have a liquid rock all the way 1,700 kilometers deep into the interior of the Earth, and then eventually the surface crust builds up, and at about 4.4 billion years ago, oceans develop. Here you have the stage for the appearance of life. We know that the solar system started from a meteorite that fell in Kazakhstan, the Movka meteorite, and from this we get an age of 4.567 billion years. Then 40 million years later, the moon formed in a collision of a Mars-sized object called Theia with the Earth. And then 4.45 billion, as I already said, oceans and continents form. And there is recently a paper in Nature which has already been mentioned, it just came out 1 or 2 weeks ago, which claims that maybe here we already have the first simple forms of life which was unlike our present known life. Then with something which I was corrected by the expert, a lot of people in the field assumed that there was this late heavy bombardment going on, and this was supposed to be nailed down with lunar observations. This bombardment had produced these very large mares on the moon, and not only was this discovered on moon, but also on Mercury, and it would have also affected the Earth and Venus, and it would have affected the Earth much more than it has, because it has 81 times the mass of the moon. Now, immediately after the late heavy bombardment, the idea is that then the progenode, the first living organism, developed, or maybe it has survived somewhere on Earth, maybe deep in the rocks from earlier epochs. 3.8 billion years, this is a reasonable age for the LUCA, the last universal common ancestor, which already had DNA as memory molecules and is the ancestor of all life, of present life on Earth. 3.8 billion years. Also 3.8 billion years, there is evidence in rocks in Greenland, from the Isoar Formation, about a special unusual C13, C12 isotope ratio, which was interpreted as being signs of life being there. This is controversial, but it seems to be logical that life must have been present at that time. Because 3.5 billion years, you have confirmed microfossils and stromatolites, which are bacterial mats, fossilized bacterial mats, and therefore this is already a very developed life, so it must have formed earlier. About the environment, we had extensive volcanism, hot, dusty, dark, a thin crust, frequent impacts. The moon was 10 times closer at those days, and therefore the tides were 1,000 times stronger than today. From sequencing of the DNA and ribosomes of bacteria, you find that those who lived at those days must have been thermophilic, heat-loving bacteria. You also think that these are halophilic, acid-loving. So you would assume a very aggressive chemistry at those times. You have, because of the dust, a lot of static electricity and discharges, electric discharges with UV radiation. And you have evaporating lagoons, which concentrates the chemistry. And so you have this gigantic chemistry lab, Earth, which produced an enormous number of organic material, which has been done in the laboratory and the Miller experiments. Now I want to tell you about why does life take so long to develop on Earth until you get intelligence here. And that is the fact, the fact is that life happens on our planet for 3.5 billion years only in the ocean. And only in the last 500 million years did life conquer the land and worked towards and formed intelligence. The reason was because from this first Luca, a prokaryotic cell, it took a tremendous time to form the so-called eukaryotic cells, which are fabulously complicated machines with internal organs called organelles, nucleus, flagellae, and so on, all kinds of peroxisomes, mitochondria, and so on and so on. So this absolutely complicated machine was the precursor, and this was roughly 1.5 billion years ago, the final stages of this development. This was the precursor for the next step of life, which was multicellular life, and which developed about 1 billion years ago. And the important thing about multicellular life is that the individual cells can specialize. So you can have liver cells, and you have brain cells, and you have skin cells, and so on and so on. And so only when you have this was it possible to conquer the land and to then subsequently develop intelligence. Only a few years ago, evolutionary biologists said intelligence is something which happens very, very seldom on Earth. It was an utter chance, you know, and a lot of books are written on this thing. But now one finds that intelligence develops in the animal kingdom on a broad basis. Already fish are quite intelligent, has been recently studied. They memorize rock formations to escape when a predator comes. Velociraptor, who has been portrayed in this Jurassic Park movie, is thought to be a turkey-sized animal, which already had feathers but couldn't fly. The flight was not developed. Not in this, and they were very intelligent. They hunted in groups, they breeded in groups, then there is another step of intelligence that can be reached, and this is so-called mirror self-recognition. What is this? If you put a mirror in front of an animal, it can recognize that this is an enemy, and react. But one finds that if you have animals above a certain intelligence, they will recognize that what looks out from the mirror are actually themselves. And this, about 2 years ago, it has been shown by crows, so-called corvids, ravens, crows, and so on, this type of bird family, that they have mirror self-recognition. They recognize themselves in the mirror. But it has also been found with capucin monkeys, dolphins, elephants, and naturally by all higher apes, like orangutan, gorilla, and chimpanzee. Chimpanzee actually is the closest being in the animal world, and it is more and more discovered how intelligent the chimpanzee is. From the line from the going to the chimpanzee and to the humans separate about 6 million years ago, and here the first beings from the time going along this hominid line were the Australopithecines. These are upright walking animals which had a brain somewhat bigger than the chimpanzee. The reason why you have upright walking was because at that time the Earth was moving towards the Ice Age, and the big rainforests in Africa receded to give way to extended savannas, and in savannas you have a lot of grass, and you have to look over the grass and see the predator approaching you, and therefore this had to be upright walking. 2 million years ago, the first humans appeared. Here I have shown you a Homo erectus. Homo erectus not only had a sophisticated Stone Age culture, but it also produced spears, hunting spears from special woods with fine peaks, and hunted, and also used fire as a tool since 1.5 million years ago. Now let me summarize what we have found so far. We have the astronomical argument that we have 4 times 10 to the 70 Earth-like planets in the universe, and we have just seen that it is most likely that life and intelligent life develops on Earth-like planets. Together, these two give you a conclusion. It is quite certain that extraterrestrial intelligent life exists. Now the problem is, why have we no contact? What is the explanation for the Fermi Paradox? And I think thinking about the nature of extraterrestrials will give you an answer. You have to pose a couple of questions. I don't want to go into this, but right away, let me start with a question. When do you expect the first intelligent beings in our galaxy? Here you have to go a little bit into the history of the galaxy. The galaxy started at the Big Bang 13.7 billion years ago, and the fireball got very quickly extinguished, and it got very quickly dark by the expansion of space, and then a dark age developed, which lasted about 200 million years until the first so-called population 3 stars formed. These were stars completely built from hydrogen and helium, and in the center, by nuclear fusion, produced heavier elements up to iron, and subsequently, in a supernova explosion, these stars were completely disrupted, and also there the other elements formed up to uranium, and this material was thrown into the hydrogen and helium gases which came from the Big Bang, and this way enriched this material. And then other stars formed, the so-called population 2 stars, which had more heavy elements. And so this went on for several generations, and eventually about 10 billion years ago, the chemical abundances of population 1 stars was formed, and therefore the first Earth-like planets, because with population 2 stars, the terrestrial planets would have too small mass. So at about 10 billion years, the first Earth-like planet came into being. And then if you say, okay, it took about 4.5 billion years till intelligence develops, you would have an estimate that 5.5 billion years ago, the first intelligent life was present in our galaxy. Now here I have shown the history of the Earth, and the Earth formed 4.6 billion years ago, and the first intelligent life of our type of intelligent life developed about 2 million years ago, which is sort of the width of this of this dashed line. So you see in this gigantic time of 5.5 billion years, this would give room for extraterrestrial civilizations. Can we imagine intelligent beings that are 1 billion years older than we? I think our brain is not good enough to ever come close to an imagination how these beings are. We can only make a sort of a comparison, a crude comparison. And that is if we compare ourselves to what had been back in the history 1 billion years ago. Let's say 1 billion years in the future, we compare it with something 1 billion years ago. And that was before multicellularity. So the difference between these extraterrestrial beings and us should be of the same magnitude in quality as the difference between us and a one-cell animal in the ocean 1 billion years ago on Earth. We should always keep this gigantic difference in mind. And if you switch on the television set at night and in the evening and you see the Stargate movies and see these Klingons or what looking at you, you will say, this is ridiculous. Now, what can we expect? How are these people, how are these intelligent beings? What can we say about them? Compared to us, they must have almost infinitely more knowledge. I mean, we have done research for 2,000 years now. They have 1 billion years of research behind them. They have, therefore, from this knowledge, an almost infinite greater power than we have. And they probably have solved mortality and all except the accidental death they will have switched off. Can we say something about the body forms of extraterrestrial life? You know that a few years ago we have decoded the human genome. And this is a 3.5 letter construction plan of a human body, and it is written in these 4 different letters. And what you find today is you have about 25,000 genes and about a similar number of switches which control the genes to, let's say, make cells, liver cells, brain cells, and so on and so on. This is a matter of the switches. And people are there to investigate and to, especially to study these switches because people want to grow organs and things like this. Now, it is quite certain that a certain stretch here, only marked as an indication, a certain stretch will tell you the construction plan of a human brain. And it's quite certain that we will soon know this construction plan, because already 50% of the genes are already known what they do. So in a few years' time, maybe 100 years or so, we will have the exact construction plan of a human brain. And as you know, every construction plan will be worked over by engineers to try to improve it. But secondly, this construction plan can be used to be translated into computer technology. And therefore androids will be built. There is no way in preventing this, and therefore we cannot predict how these extraterrestrial intelligent beings look like. It's quite impossible to predict. They are very likely inorganic, miniaturized, and maybe have even a free choice of their body. Let's have more questions. Can we say something of the average lifespan of such a civilization? This is a difficult question because we don't even know it for ourselves. Can we say something about the number of ET civilizations in our galaxy? This was your prime interest, your prime motivation for your Drake equation. the impact, the lifespan, depends on how easy it is that a civilization dies. There are external dangers. Remember the dinosaurs which were killed by asteroid impact? I don't think these are dangers which today we have to seriously consider, because if an impact is imminent, we could try to destroy the impactor, or we could hide and then just suffer the consequences, but I think human beings will not be extinguished because of this. I think the only and greatest and most the most dangerous thing is that with increasing knowledge, we are getting increasingly more powerful to destroy ourselves. And this is the internal thing. And this is the only danger which grows with time. The more human beings understand, the more there are possibilities to kill. And so how can we make an estimate? We can say, well, we have already discussed that maybe these beings which came about very early in the history of the universe, who are 10 to the 9 years old, are still around. This is the optimist view. And the pessimist will say, oh, we will not survive the next 1,000 years. We will surely kill ourselves if we continue the way with Hitler and bin Laden and the other nice guys. So we will not survive more than 1,000 years, but we have already lived 2 million years. So you have these two numbers, and you can make a logarithmic mean between these numbers. You come up with some reasonable or some unreasonable number, and the guess is, let's say, 10 to the 7 years. Okay, if this is the lifetime, what does follow from this? Here you have plotted the number of Earth-like planets versus time. And we said the first Earth-like planet developed about 10 billion years ago, and it increased, and if the rate of formation of Earth-like planets was sort of continuous over time, we have today 4 times 10 to the 6 Earth-like planets, as I had derived. I mean, all these numbers are naturally not very certain. But now we see that first intelligent life came about 5.5 billion years ago, but then in 10 to the 7 years, in 10 million years, it died. Then other planets came about, and then this life died too, and so on and so on. And this whole blue regions are all intelligent civilizations which later had died under the assumption that they only lived 10 to the 7 years. And the only intelligent civilizations surviving were formed by planets which have been created 10 million years earlier than the Earth. And so they survive to today, and this is a very tiny number of only 40,000 civilizations, which should be presently alive in the galaxy. Now,
4,000 or 40,000?
4,000. Excuse me, did I say 40? 4,000. 4,000 only. Now, can we say something about how far away they are to see whether they could come here? And could we say whether we can they identify us? That could be a reason why they have not come here. Now, to estimate the distance of the next alive civilization in our galaxy, you take the galaxy as a big box which a diameter of 100,000 light years and a thickness of 1,300 light years, and in this box you throw now 4,000 planets, and distribute them equally, and then measure or calculate the distance between two, and you find 1,700 light years. This is the reason why SETI hasn't found much, according to my opinion. Yeah? This is very far away. And now, is the problem of these beings that they don't know where we are? This can be answered with this picture here. This is the infrared spectra from the solar system, and you see the Venus, you see Earth and Mars in the infrared, and you see the very big carbon dioxide bands here in all of these planets, but only on Earth do you have the water vapor band, and this water vapor band is already there since 4.4 billion years, so it cannot be overlooked for a very long time. And also already ozone is there, which is a sure sign of life, and it's there already since 2.5 billion years. Now in a few years' time we will be able to resolve all the terrestrial planets on all stars of our Milky Way with gigantic telescopes floating in the solar system and communicated with laser beams, and we will be able to see the infrared spectra of these planets in a few, let's say 100 years or so, and therefore we'll know on which planet in our galaxy life exists. Let me come to the last slide. We have learned about extraterrestrial intelligent civilization that compared to us, they are almost omniscient. Compared to us, they are imaginably advanced technologically. Therefore, there is absolutely no problem contacting us and visiting us, because they are essentially immortal. But we have also learned with this very advanced knowledge comes the extreme danger of self-destruction. And only those societies will survive which have developed a stable, responsible civilization to master this danger. And therefore, from these beings, you cannot expect irresponsible behavior. Now, there is a sole hypothesis which explains the Fermi Paradox. It says, developed by Ball and Sagan, they know where we are, but they don't want any contact. Because a contact would be extremely irresponsible. Just think what would happen. Something much worse would happen than happened to the American Indians when Columbus came. We would have to forget all what we have learned in science, yeah, because they have a billion-year more science than we could forget all of our cultural and Mozart and so on, because they have so much more and bigger things. And this would be a tragedy, because we would have to forget our own destiny and our own things, and we could never show what could become of us in a billion years' time. It would be utterly irresponsible, and it cannot be expected from these aliens, that they will contact us, because if they would be capable of irresponsibility, they would long have killed themselves. Let me summarize what I said. I said extraterrestrial intelligent beings exist. They avoid all contacts. And actually I claim that they observe us, because Intelligent societies are the most interesting things in our galaxy. Black holes, they know since billions of years, nothing mysterious, and even asteroids and so on. But intelligent societies are very individualistic, are very scarce in our galaxy, and therefore we must be intensely interesting, probably the only very interesting thing in our galaxy. And now you will say, the guy has lost a screw up here. I claim that they are here on Earth, or maybe in the solar system. My reasoning is the following thing. The only time when these beings might be tempted to intervene would be when there would be a super bin Laden here to press the red button and kill all of mankind. They would have observed it for 2 million years and to see what comes out of us, yeah? What will develop out of us. And then one guy will finish the experiment. Now, in order to prevent this, they might actually be tempted to change this guy a little bit without him knowing it. Yeah? But in order to do that, they cannot observe from 1,700 light years away. Because if they would then come, the whole thing would be finished. Yeah? They can only do it if they were here. And so I claim they are here. Thank you very much.